The great void, where the universe becomes silent. There are places in the universe where almost nothing exists. No stars burning, no galaxies spinning, no clouds of glowing gas. Only distance, only silence, only space stretching so far that even gravity seems to lose its voice. Tonight, we begin our journey into those places, not to witness destruction, not to chase spectacle, but to drift slowly into the quietest regions the universe has ever formed. Astronomers call them cosmic voids, vast regions between the filaments of galaxies, where matter is so sparse that light itself becomes rare. On the largest maps of the universe, these voids appear like dark bubbles, surrounded by glowing walls of galaxies, but inside them there is almost nothing at all. To understand how these immense empty regions came to exist, we need to step back, far beyond human history, far beyond the formation of stars, to a time when the universe itself was young. In the first moments after the Big Bang, the universe was not structured. It was hot, dense, and nearly uniform, with matter spread almost evenly in all directions. But almost is the key word. Tiny fluctuations in density, imperceptible differences in temperature and matter were already present. These minute variations, measured today in the cosmic microwave background, became the seeds of everything that followed. Where matter was slightly denser, gravity began its slow work. Regions pulled inward, growing heavier over millions and then billions of years. These became the filaments and clusters of galaxies. And where matter was slightly less dense, gravity had less to gather. Those regions were left behind, slowly emptying as surrounding matter flowed away. Over cosmic time, these underdense regions expanded, stretching larger and emptier, becoming the great voids we observe today. The universe did not place these voids deliberately. They are not gaps carved by violence. They are the natural consequence of gravity doing what it always does, pulling matter together elsewhere. As galaxies formed along dense filaments, the voids quietly grew in between, like silence forming between notes of a song. Today, the largest voids span hundreds of millions of light years. Some are so vast that if you were placed at their center, the nearest galaxy would be farther away than any object visible to the naked eye from Earth. One of the most famous of these regions is the Boötes Void, discovered in the early 1980s. It stretches roughly 330 million light-years across. Inside it, there are only a handful of galaxies, where thousands should exist. Astronomers sometimes describe it as one of the emptiest places ever discovered. But emptiness in cosmology is never absolute. Even inside the deepest void, there are still particles drifting, dark matter flowing invisibly, and faint radiation passing silently through. The void is not nothing, it is almost nothing, and that distinction matters. Because the great void is not simply a lack of content, it is a structure, a feature, a fundamental part of how the universe organizes itself. Without voids, there would be no cosmic web. Without emptiness, there would be no structure. The universe, it turns out, is shaped as much by what is absent as by what is present. As we drift deeper into these quiet regions, a natural question arises. What would it feel like to exist there? Imagine floating in a place where stars are absent, where the sky is nearly black in every direction, not because something blocks the light, but because there is almost none to begin with. No Milky Way stretching overhead, no distant galaxies forming faint smudges. Only darkness, broken occasionally by a single point of light millions of light years away. Time would feel different. Without nearby stars, there would be no familiar rhythms, no orbits to mark passing ages, no explosions, no creation events. Only slow expansion as space itself continues to stretch. The void is not static, it grows. As dark energy pushes the universe to expand faster, voids expand even more rapidly than dense regions. They become emptier, colder, and quieter over time. In this sense, voids may represent the future of the universe. As galaxies drift farther apart, as stars burn out, as energy spreads thin, the universe may become increasingly a vast void, punctuated by isolated islands of matter, a slow fade into silence. But long before that distant future, the great void already exists, patient and immense, surrounding every galaxy, including our own. The Milky Way itself lies on the edge of a modest void, part of a delicate balance between emptiness and structure. We are not at the center of the universe, but we are always close to nothing. And perhaps that is fitting, because emptiness in cosmology is not failure. It is not absence of meaning. It is the canvas upon which everything else appears. In the next part of our journey, we will drift further into these silent regions and ask deeper questions. Does emptiness have structure? Can voids teach us about dark energy? And what does the universe look like when we remove almost everything from it? For now, there is nothing you need to do. Just drift. Just listen to the silence between galaxies. When astronomers first began mapping the universe on its largest scales, they did not expect to find emptiness. They expected complexity. They expected randomness. They expected galaxies scattered through space like grains of sand. What they found instead was a pattern, a structure so vast that it can only be seen when millions of galaxies are plotted together, their positions reduced to points of light on an unimaginable canvas. This structure is known as the cosmic web. Galaxies are not distributed evenly. They form long filaments, thin bridges of matter stretching across hundreds of millions of light years. These filaments intersect at dense nodes where galaxy clusters gather, held together by gravity and dark matter. And between these glowing threads, there are enormous regions of absence, the voids. At first glance, these voids might seem like mistakes in the map, places where data is missing or observations failed. But as surveys grew larger and more precise, the voids remained. Again and again, across every direction of the sky. They were not artifacts, they were real. By the early 2000s, projects like the Sloan Digital Sky Survey had mapped millions of galaxies, revealing the universe in unprecedented detail. When these maps were visualized, the result was unmistakable. A universe shaped like foam. Dense walls and filaments surrounding vast bubbles of near emptiness. These bubbles are the great voids. Each one is different. Some are relatively small, only a few tens of millions of light years across. Others are immense, spanning distances so large that light itself takes hundreds of millions of years to cross them. What defines a void is not complete emptiness, but extreme scarcity. In an average region of the universe, you might find several galaxies within a given volume of space. Inside a void, that number drops dramatically, sometimes by a factor of 10, sometimes by a factor of 100. In the deepest voids, there may be only one lonely galaxy where thousands should exist. This raises a quiet but profound question. Why did matter leave these regions behind? The answer lies in gravity, but not in the dramatic sense we often imagine. There were no explosions that carved the voids, no forces pushing matter outward violently. Instead, matter simply followed the path of least resistance. In regions that began slightly denser, gravity pulled matter inward, strengthening itself over time. In regions that began slightly emptier, there was less gravity to hold matter in place. So matter drifted away, slowly, patiently, over billions of years. The voids emptied not because something pushed matter out, but because nothing held it in. This process is still happening. Even today, galaxies near the edges of voids are slowly moving outward, away from the void centers, drawn toward denser filaments beyond. If you could watch the universe in extreme slow motion over billions of years, you would see the voids breathing, expanding, stretching, growing quieter. In a sense, voids are the most honest expression of cosmic expansion. They are regions where matter has largely surrendered its influence. And this makes voids uniquely valuable to scientists. Because in places where matter is scarce, its effects are easier to isolate. Voids become laboratories for studying the underlying forces shaping the universe. Dark matter, for example, still flows through voids. It does not disappear, it simply becomes thinner, more diffuse. Simulations show that even in the deepest voids, dark matter forms faint filaments, delicate structures too subtle to host galaxies, but present nonetheless. Dark energy, too, reveals itself more clearly here. As space expands, voids expand faster than dense regions. They are less restrained by gravity, more responsive to the stretching of space itself. By observing how voids grow and evolve, scientists can test theories of dark energy with remarkable sensitivity. This brings us to another question, one that feels less scientific and more personal. How does the idea of such vast emptiness make you feel? Some people find it unsettling, a reminder of insignificance, of isolation. Others find it calming, a place free from chaos, free from noise, free from urgency. If you imagine yourself drifting through one of these voids, with no nearby stars, no familiar constellations, what emotion arises first? Is it loneliness or peace? There is no correct answer, and if you feel inclined, you can share your thoughts quietly in the comments below. The universe, after all, does not judge our interpretations. It simply exists. And as we continue our journey, the voids will invite us to listen more closely. Because sometimes the most important structures in the universe are defined not by what they contain, but by what they lack. In the next part, we will drift deeper still and explore what happens when we remove almost everything and look at what remains. To truly understand the Great Void, we need to shift our perspective. Instead of asking what is missing, we begin to ask what remains. Even in the quietest regions of the universe, where galaxies are rare and light is scarce, there is still structure unfolding slowly beneath the surface. This structure is shaped largely by something we cannot see: dark matter. Although voids appear empty to our eyes, they are not empty of dark matter. They are simply regions where it is stretched thin. Computer simulations of the universe, run on powerful supercomputers, reveal that dark matter forms a delicate framework everywhere, even inside voids. The difference is density. In galaxy clusters, dark matter piles up, forming deep gravitational wells. In voids, those wells are shallow, barely able to hold on to ordinary matter. As a result, gas does not collapse easily, stars do not ignite, galaxies struggle to form. Yet dark matter is still there, flowing slowly, tracing faint filaments like whispers of structure. These simulations are not abstract guesses. They begin with precise measurements of the cosmic microwave background, the faint afterglow of the Big Bang. Those tiny temperature variations, only one part in 100,000, set the initial conditions for everything that followed. When dark matter is included, the simulations produce a universe that looks remarkably like the one we observe. Filaments, clusters, and vast voids in between. When dark matter is removed, the universe fails to form recognizable structure. The voids themselves tell us something profound. They are not accidents. They are evidence that dark matter has guided matter away from these regions, toward denser gravitational centers. In a way, voids are shaped by absence, but absence created by invisible presence. This leads to another quiet question. If dark matter exists everywhere, why does it allow such emptiness to persist? The answer lies in balance. Dark matter interacts primarily through gravity. It does not collide, it does not radiate, it does not clump easily unless conditions are right. In voids, those conditions never fully arrive. Gravity is too weak, matter too sparse. So the void remains. Over time, as cosmic expansion accelerates cosmic expansion, these regions become even more isolated. Void interiors grow colder, more diffuse, more silent. Some physicists believe that voids may be the cleanest places in the universe to test fundamental laws of physics. With so little matter to interfere, subtle effects become easier to detect. Does gravity behave exactly as predicted? Does dark energy act uniformly, or does it vary slightly from place to place? Voids may hold the answers. And yet, for all their scientific value, voids also invite reflection. Consider the idea that most of the universe's volume is composed not of galaxies, but of emptiness. Everything we have ever seen, every star, every planet, every living being, occupies only thin threads within an ocean of near nothing. How does that make you feel? Does it change the way you think about importance, about scale, about presence? Some people find this perspective humbling. Others find it strangely comforting. If you wish, you can share how this idea resonates with you in the comments below. There is no need to be certain. There is no need to be profound. Even quiet thoughts belong here. As we continue drifting through the great void, we will begin to explore an even deeper idea, that emptiness itself may be one of the most powerful forces shaping reality. And in that silence, the universe may be telling us more than noise ever could. As we drift deeper into the great void, the universe begins to feel less like a place and more like a condition. Here, Distance dominates everything. Space stretches without interruption, and the familiar landmarks of the cosmos fade away. In regions filled with galaxies, gravity constantly competes with expansion. Stars pull on stars, galaxies tug on one another, structure resists separation. But inside the void, that resistance weakens. There is simply less matter to argue with the expansion of space itself. This is why cosmologists often describe voids as the most sensitive regions of the universe to the influence of dark energy. Dark energy, the mysterious force driving accelerated cosmic expansion, does not act selectively. It permeates all of space. Yet its effects are easier to observe where gravity is weakest. In dense clusters, gravity still holds galaxies together, masking the subtle push of expansion. In voids, there is little to hold things back. Space stretches more freely. Distances grow faster. The voids expand from within. Some researchers describe voids as cosmic magnifying glasses for dark energy. By studying how voids change shape over time, how their boundaries evolve, and how quickly galaxies retreat from their centers, scientists gain insight into the nature of expansion itself. Large surveys have begun to use voids as tools rather than curiosities. Instead of ignoring emptiness, they measure it carefully. How round is a void? How elongated? How does its size change with distance and therefore with cosmic time? These measurements may seem subtle, but over millions of light years, small differences accumulate into meaningful signals. In some models, voids grow faster than predicted. In others, their shapes hint at deviations from standard gravity. So far, the simplest explanations still hold, but the quiet nature of voids makes them ideal places to listen for new whispers of physics. There is another layer to this story, one that feels almost philosophical. If most of the universe's volume is emptiness, what does that say about existence itself? We tend to focus on objects, on stars, on planets, on things we can name. But the universe seems to suggest that absence is just as fundamental. Without voids, matter would have nowhere to go. Without emptiness, structure could not form contrast. The cosmic web relies on tension between fullness and lack. This balance shapes everything. Even our own galaxy owes its position to the surrounding voids, which gently influence its motion through gravitational imbalance. We are not isolated. We are guided subtly by emptiness. Imagine for a moment standing at the boundary between a filament and a void. On one side, a dense river of galaxies, glowing and dynamic. On the other, a vast, dark expanse, quiet and almost timeless. Which side would feel more alive? The answer is not obvious. Life thrives in structure, but peace often resides in stillness. Perhaps the universe offers both, not as opposites, but as complements. If you picture yourself drifting slowly into the void, leaving behind the crowded regions of space, what do you feel first? Relief? Curiosity? A faint unease? You can pause with that question. There is no need to resolve it. Some viewers share that imagining the void helps quiet their thoughts. Others find it unsettling, a reminder of how small and temporary we are. Both reactions are natural. And if you feel inclined, you can leave a quiet reflection below the video. What does emptiness mean to you when it stretches across the universe itself? As we continue, the great void will reveal something unexpected. That emptiness is not passive. It evolves, it grows, it shapes the destiny of the cosmos just as surely as the brightest stars. And in that realization, the silence becomes meaningful. As we remain within the great void, the sense of scale begins to change. Not because the void suddenly becomes larger, but because our awareness quietly adjusts. In regions filled with galaxies, motion is easy to notice. Stars orbit, gas swirls, galaxies merge, separate, and reshape one another. Light flares, fades, returns. Inside the void, change happens differently. Here, transformation unfolds so slowly that it almost escapes notice. Space stretches without drama. Distances increase without announcement. Time seems to loosen its grip. Cosmologists often describe voids as regions where the universe reveals its long-term intentions, not through violence, but through patience. The expansion of space affects every corner of the cosmos, but nowhere is it easier to trace than here. In dense clusters, gravity continues to bind matter together. Galaxies remain locked in slow dances. Local structure resists separation. Inside voids, that resistance weakens. There is simply less mass to hold space in place. As a result, voids expand faster than their surroundings, not explosively, but persistently. Over billions of years, this difference becomes measurable. The edges of voids drift outward. Galaxies near their boundaries migrate toward denser filaments. The interiors grow quieter, emptier, more dominated by space itself. This makes voids powerful tools for understanding dark energy. Dark energy does not glow, it does not collide, it does not leave footprints in light. It reveals itself through motion, through the way distances change over time. By measuring how voids expand, how their shapes evolve, and how matter flows around them, scientists can test whether our standard model of cosmology is complete. So far, observations suggest that dark energy behaves consistently, pushing space apart at an accelerating rate. But questions remain. Is dark energy truly constant, like a steady background pressure? Or does its influence change slowly over cosmic time, subtly reshaping the expansion history of the universe? Do voids expand the same way everywhere, or are there small variations, gentle differences hidden within the silence? These questions are difficult to answer in crowded regions of space, where gravity, gas physics, and galaxy evolution add layers of complexity. But inside the void, the universe speaks more clearly. Less interference, less noise, less confusion. There is another reason voids matter. They allow us to imagine the far future of the cosmos. As dark energy continues its quiet work, galaxies will drift farther apart, clusters will thin, interactions will become rarer. Over unimaginably long timescales, the universe may resemble a vast void punctuated by isolated islands of matter, regions that remain gravitationally bound, surrounded by expanding darkness. Stars will burn out, white dwarfs will cool, neutron stars will fade, and black holes over staggering timescales may slowly evaporate through Hawking radiation. Light itself will become scarce, not because it is destroyed, but because it travels into distances where it can no longer reach anything that can respond. In this distant future, an observer, if any still exist, might look up and see almost nothing. No glowing band of the Milky Way, no nearby galaxies, no familiar constellations, only a few dim remnants, and beyond them, silence. It is tempting to think of this as an ending, but cosmology suggests something more subtle. Not an end,
but a transformation. The universe does not collapse into nothingness, it relaxes into simplicity. Structure fades, motion slows, differences even out. What remains is space, time, and the quiet persistence of physical law. Some physicists describe this as the universe approaching equilibrium, a condition where nothing dramatic happens because there is little left to interact. From a human perspective, this may feel unsettling. We often associate meaning with activity, with creation, with bright events. But the universe does not share our preferences. It is content to be still. Perhaps this challenges how we think about emptiness. We often treat emptiness as absence, as a lack of value. But on cosmic scales, emptiness is not failure, it is outcome, the natural result of expansion, gravity, and time. And when you imagine drifting within a vast void, with no stars nearby, no landmarks to orient yourself, what sensation arises? Do you feel lost, or do you feel free? Without reference points, without expectations, existence becomes simpler. There is no direction to rush toward, no event demanding attention, only the present moment, extended across immense distances. Some listeners describe this imagined void as deeply calming, as if the mind finally has room to breathe. Others find it uncomfortable, a confrontation with silence. Both reactions are valid. And if you feel inclined, you may share your thoughts quietly in the comments below. What does a universe growing quieter mean to you? As our journey continues, we will move even deeper into the void, toward regions where structure fades almost completely. There, we will ask whether emptiness is truly empty, or whether it hides subtle forms of order that we have yet to understand. For now, there is nothing to resolve, only space stretching gently and time flowing without urgency.
If we continue drifting through the great void, the next thing we notice is not what we see, but what we stop seeing. Fewer galaxies, fewer faint smudges of light, fewer distant points that suggest a story happening somewhere else. And in that quiet reduction, another idea comes into focus. The void is not only an emptiness of matter, it is also an emptiness of signals. In dense regions of the universe, light is constantly being produced by stars, by hot gas, by energetic events like supernovae, and by matter falling into black holes. Those regions are loud in radiation. They glow in visible light, in infrared, in X-rays, in radio waves. But in the interior of a cosmic void, the universe becomes less radiant and therefore easier to interpret in certain ways. This is why astronomers often treat voids as natural laboratories, not because nothing happens, but because fewer things happen at once. When the cosmos is crowded, signals overlap, background noise increases. Cause and effect are difficult to separate. Inside the void, the universe becomes simpler. This simplicity has made voids increasingly valuable for a specific kind of measurement, the behavior of gravity on the largest scales. We typically assume gravity follows the same rules everywhere. Newton's gravity works well for many situations. Einstein's general relativity extends that picture, describing gravity as the curvature of space-time. On cosmic scales, our best model uses general relativity along with dark matter and dark energy. It is remarkably successful, and yet, because dark energy is mysterious and dark matter remains undetected directly,
some researchers continue to ask a gentle, persistent question. What if the universe is not filled with invisible substances, but governed by a slightly different kind of gravity? This is where voids become important. If gravity behaves differently at very low accelerations, as some modified gravity theories propose, then the emptiest regions of the universe should reveal the differences more clearly. Dense clusters can hide subtle deviations. Voids' interiors cannot. So astronomers have begun to use voids to test whether the standard model of cosmology holds up under the quietest conditions. They look at how galaxies move around voids. They measure how voids distort background light through weak gravitational lensing. They map the outflow pattern, the tendency of matter to drift away from void centers and toward denser filaments. In the standard picture, voids grow as matter drains out, and their edges become sharper over time. In some alternative theories, voids would grow differently, or their lensing signatures would not match predictions. The results so far tend to support the standard model, but not perfectly. There are tensions and open questions, subtle mismatches that could be measurement limitations or could be hints of something deeper. And this is part of what makes the great void so quietly intriguing. Another observational clue comes from the cosmic microwave background, the faint afterglow of the Big Bang. As CMB photons travel through the universe, they pass through regions of different gravitational potential. They fall into gravitational wells and climb out again. If the universe were not accelerating, the net energy change would cancel out. But because dark energy causes expansion to accelerate, gravitational potentials slowly change with time. This creates a subtle effect. CMB photons can gain or lose a tiny amount of energy, depending on whether they pass through a cluster or a void. When photons pass through a void, the changing gravitational landscape can make them emerge slightly cooler, producing a faint, cold spot signal correlated with void locations. This is called the integrated Sachs effect. It is not easy to measure. The signal is extremely small, but it is another way the universe allows us to see the imprint of voids without using visible matter. Voids, in a sense, leave shadows on ancient light. This brings us to a deeper, almost poetic point. The universe does not always speak through brightness. Sometimes it speaks through absence, through subtle temperature shifts, through gentle distortions, through patterns that only appear when millions of measurements are combined. And that is what modern cosmology often feels like, a quiet listening. Now, there is a question many people naturally ask here. If voids are emptier than average, are they truly empty? The honest answer is no. Even the deepest voids contain faint traces of gas, a thin scattering of dark matter, and sometimes small, dim galaxies that survive in relative isolation. These void galaxies are fascinating because they evolve differently. In crowded regions, galaxies are influenced by neighbors. They merge, they collide, they are stripped of gas, they are stirred by tidal forces. In voids, galaxies can grow more slowly, keeping their gas for longer, forming stars at a gentler pace. They are not necessarily older, but they can be less disturbed. Studying them helps astronomers understand how environment shapes galaxy evolution, and it also raises a quiet possibility. If life ever emerged elsewhere in the cosmos, would it prefer the crowded regions, rich in heavy elements and energetic events, Or would a calmer environment, with fewer catastrophic encounters, offer a more stable cradle? There is no answer here, only a thought. If you were choosing a home for a long-lived civilization, would you choose a busy cosmic city or a quiet cosmic countryside? If you have a feeling about that, you can share it in the comments below. As we move on, the Great Void will ask us to think about something subtle, not just the emptiness of space, but the emptiness of information. How do we know what we know when the signals become faint? And what might we be missing simply because the universe is too quiet to be heard easily? For now, we continue drifting, breathing, letting the distances widen, and allowing the silence to feel less like nothing and more like space itself, holding the shape of reality.
As we drift onward, the Great Void begins to reveal a quiet paradox. The emptiest regions of the universe are not the places where physics becomes irrelevant. They are the places where physics becomes clean. In crowded space, we are surrounded by complications. Gas heats and cools, stars ignite and explode. Magnetic fields twist, shock waves pass through interstellar clouds. Black holes flare, then fade. All of these processes are fascinating, but they overlap. They blur one another. They make it difficult to isolate the simplest forces. Inside the void, many of these effects diminish. Less gas, fewer collisions, fewer violent events. And so the most basic forces become easier to trace. Gravity, expansion, and the subtle growth of structure over time. This is why voids have become central to a modern kind of cosmology, one that is less about dramatic objects and more about statistical patterns. To map a void, astronomers do something humble and powerful. They count. They measure the positions of galaxies across enormous volumes of space. They identify regions where the density is unusually low. They trace the boundaries where filaments and walls begin to appear, and then they study how those regions behave. At first glance, a void may seem like a simple hole in the cosmic web, but it is more like a landscape. It has slopes where matter drains outward. It has ridges where filaments mark the edges. It can have smaller voids inside it, nested emptiness within emptiness, like quiet layers. Simulations of cosmic evolution suggest that voids are not static. They merge, they expand, they reshape one another, slowly, over billions of years. Sometimes two neighboring voids grow until the thin wall between them dissolves and the emptiness becomes one larger region. This merging is the quiet counterpart to galaxy mergers. In dense space, structures collide and combine. In empty space, absence itself combines. This is not just a poetic image, it is a measurable prediction. Large surveys have now mapped thousands of voids, and their statistics, sizes, shapes, distributions, can be compared with simulations. When those patterns match, it strengthens our confidence that we understand the fundamental ingredients of the universe. When they do not match, the void becomes a question mark. One of the most important measurements here relates to the geometry of space. There is a classical idea in cosmology called the Alcock-Paczynski test. The concept is simple. If you know that an object is, on average, spherical, you can use its apparent shape to measure the expansion of the universe. A perfect sphere will look distorted if your assumptions about cosmic distances are wrong. Voids, when averaged over many examples, are expected to be nearly spherical. So if a survey observes that voids are systematically stretched along the line of sight or compressed, this can reveal information about the universe's expansion history. This test is quiet but powerful. It uses emptiness as a ruler. It turns the absence of galaxies into a measurement of cosmic geometry, and in doing so, it links the Great Void to the deepest questions in physics. What is the shape of space-time? How does it evolve? What is the true nature of acceleration? Another question emerges when we think about voids. How does time flow through such regions? Not in the philosophical sense, but in the gravitational one. General relativity tells us that gravity affects time. Clocks tick more slowly in stronger gravitational fields. They tick more quickly where gravity is weaker. In principle, a clock inside a deep void would experience a slightly different gravitational environment than a clock inside a dense cluster. The difference is extremely small, far beyond anything we can measure directly with human instruments. But as an idea, it is striking. Voids are regions where the universe is not only emptier, but slightly closer to gravitational freedom, a place where space-time is less curved, less compressed by mass. It raises a gentle image. In the Great Void, the universe breathes a little easier. Now, there is a subtle observational phenomenon that connects to this idea of breathing space-time. It is sometimes called redshift space distortions. When we measure the distance to galaxies, we often rely on their redshift, the stretching of light as the universe expands. But redshift contains two effects mixed together: cosmic expansion and the galaxy's own motion. In dense regions, galaxies fall inward toward clusters. In voids, galaxies tend to flow outward, away from emptiness and toward structure. These peculiar velocities create patterns in redshift space. Clusters appear elongated, like fingers pointing towards us. Voids have their own signatures, subtle stretching and squashing effects that reveal the outflow of matter. By measuring these distortions statistically, astronomers can infer how fast structure is growing in the universe, and that growth rate is sensitive to both dark energy and gravity. If gravity behaves differently on large scales, the outflows around voids would change. If dark energy evolves over time, void growth would change. So once again, voids become a place to listen, a place where the universe whispers its rules. There is a quiet kind of wonder here. We often imagine discovery as dramatic, a new planet, a bright explosion, a sudden signal. But void cosmology is different. It is the science of faint patterns, tiny distortions in galaxy shapes, small statistical shifts in void geometry, subtle temperature differences in ancient light. And yet these faint patterns carry enormous meaning. They tell us that the universe is organized, that its emptiness is not random, but structured, shaped by gravity and expansion over cosmic time. If you pause and consider this for a moment, it can feel almost intimate. The cosmos is vast, and yet its rules are consistent enough that even silence has structure. What does that do to your sense of perspective? Does it feel comforting to know the universe follows patterns? Or does it feel strange that even silence has structure? If you have a thought, you can share it below. A simple sentence is enough. As we continue into next part, we will move from the measurement of voids to a more speculative question.
whether the Great Void is simply a feature of the cosmic web, or whether in some cases it might hint at something rarer, something less expected, a kind of cosmic anomaly that makes scientists pause and look again. For now, we remain in the quiet. Let the expansion continue. Let the distances widen, and let the emptiness feel less like nothing and more like a geometry holding reality in place.
There is a moment in many scientific stories when the evidence is strong, the patterns are consistent, and yet a quiet uncertainty remains. Not because the data is wrong, but because nature has more than one way to create a similar effect. The Great Void brings us to that kind of moment. So far, we have treated voids as natural outcomes of gravity and expansion, the low-density regions of the cosmic web, formed as matter flowed toward denser filaments and clusters. This picture is widely accepted and strongly supported by simulations. But the universe has a habit of leaving room for rare exceptions. And so, when astronomers encounter a void that is unusually large, unusually empty, or oddly shaped, another question appears. Could some voids be more than ordinary emptiness? Could they be signs of something unusual in the history of the universe? The most famous example of this curiosity is sometimes called the cold spot. It is a region of the cosmic microwave background that appears slightly colder than average. The temperature difference is tiny, only tens of microkelvin, but the region is large on the sky, large enough that it has inspired debate. One possible explanation is straightforward. A large supervoid along our line of sight could imprint a cold spot on the CMB through the integrated Sachs-Wolf effect. In simple terms, photons crossing a deep underdensity experience a changing gravitational environment in an accelerating universe, and they can emerge slightly less energetic. A shadow cast not by dust or gas, but by the geometry of space-time. Some surveys have found hints of an underdense region in that direction, suggesting a supervoid might contribute. But the story is not fully settled. Other analyses suggest the void is not deep enough to explain the full temperature anomaly. And there is another possibility. Perhaps the cold spot is simply a statistical fluctuation, a rare but natural feature of a random field. The universe, after all, contains randomness. Even in the quiet patterns of the CMB, some regions will be more extreme than others by chance alone. Still, the cold spot remains a reminder. Sometimes emptiness can look like a message, and sometimes it is just a coincidence. This leads to a broader question that cosmologists explore. Could there be rare features in space-time, ancient imprints from the early universe that show up today as unusual voids? One speculative idea involves topological defects like cosmic strings or textures, hypothetical remnants of early universe phase transitions. These are not confirmed, and they may not exist, but they represent a class of possibilities. Structures in the fabric of reality that could influence matter distribution and create unusual patterns. Another idea, even more speculative, is that some large-scale anomalies could be related to events beyond our observable horizon. If the early universe underwent inflation, it expanded rapidly, stretching tiny quantum fluctuations into the seeds of cosmic structure. Inflation explains many observations elegantly, but it also raises a question. If inflation happened, could it have happened differently in different regions? Could there be patches of the universe with slightly different histories, leaving subtle fingerprints in the CMB and large-scale structure? These questions are difficult to test, and most scientists treat them cautiously. Yet the Great Void invites them because it is a place where typical structure thins out and unusual features become easier to notice. There is a gentler kind of speculation too, one grounded not in exotic physics, but in the limits of measurement. When we map the cosmic web, we are not seeing the universe directly. We are seeing the galaxies, which are luminous tracers of a larger, mostly invisible distribution dominated by dark matter. A void in galaxies is not necessarily a void in dark matter. Often, dark matter still forms faint filaments through voids, thin scaffolds that do not host many visible galaxies. In other words, some emptiness could be partly an illusion, created by how light traces matter. This is why surveys and simulations must work together. We compare the galaxy distribution with predicted dark matter distributions, and we use gravitational lensing to detect mass directly. Even so, the map remains imperfect, and imperfections can sometimes look like mysteries. This brings us to a more personal kind of question, the kind that fits quietly into a sleep-friendly documentary tone. How often do we mistake absence for meaning? When we see a gap, a silence, an empty space, we tend to interpret it. We imagine a cause, a story, a hidden truth. Sometimes we are right. Sometimes the gap is a signal, a clue that something is missing from our model of reality. But sometimes the gap is simply part of the natural pattern, neither warning nor secret, just how things turned out. The Great Void is a teacher of this patience. It reminds us that science advances slowly. A single anomaly does not overturn a theory. It invites careful checking, better data, more surveys, independent confirmation. And when the anomaly persists, it becomes a doorway. When it disappears, it becomes a lesson in humility. If you think about the cold spot or about unusually large voids, what do you feel most strongly? Curiosity? Skepticism? Wonder? There is no correct response, but if you want, you can share your sense in the comments below. Do you feel that cosmic anomalies are likely to be new physics, or mostly the natural extremes of randomness? As we move toward the next file, we will step back from anomalies and return to something more universal. The experience of living inside a structured universe where most of the volume is empty, and yet that emptiness shapes everything. For now, we stay with the quiet possibility that even in the most silent regions of space, the universe may still be leaving faint signatures, not loud enough to demand belief, but gentle enough to keep us listening.
After considering anomalies and rare exceptions, it can be comforting to return to what we can measure reliably. Not because measurement ends mystery, but because it gives mystery a steady frame. In the Great Void, that frame is built from patterns, subtle patterns, quiet patterns, patterns that only emerge when we look at the universe as a whole. One of the most useful patterns is called baryon acoustic oscillations, often shortened to BAO. The name sounds technical, but the idea can be carried gently. In the early universe, before stars formed, everything was hot, dense, and filled with light. Ordinary matter, protons and electrons, was coupled to radiation. Photons and matter pushed and pulled each other in a kind of shimmering pressure wave. These waves expanded outward from tiny overdensities, like ripples in a pond, except the pond was the universe itself. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral atoms. Light decoupled from matter. The pressure waves stopped being driven, but their imprint remained. A slight preference, a faint ring of separation scale where galaxies would later be a little more likely to form because matter had been nudged outward in those ancient ripples. Today, billions of years later, that ancient scale still exists as a statistical feature in the distribution of galaxies. It is not visible as a ring you can point to in the sky, but it appears in the way galaxies cluster and in the typical separation between large-scale structures. Cosmologists use this as a standard ruler. If you know the true size of that ruler, you can compare it to how large it appears at different distances and learn how the universe has expanded over time. Now, here is where voids quietly return to the story. Voids are not separate from BAO, they're part of the same large-scale landscape. The cosmic web is a combination of overdense filaments and clusters and underdense voids between them. When surveys map galaxies across enormous volumes, they are mapping both structure and emptiness at once. And because voids grow and shift with expansion, their statistics can complement BAO measurements. This is a very gentle but important point. We do not learn cosmology from a single object. We learn it from the way millions of objects and millions of empty regions arrange themselves. In that sense, the Great Void is not just a feature, it is part of the After considering anomalies and rare exceptions, it can be comforting to return to what we can measure reliably. Not because measurement ends mystery, but because it gives mystery a steady frame. In the Great Void, that frame is built from patterns, subtle patterns, quiet patterns, patterns that only emerge when we look at the universe as a whole. One of the most useful patterns is called baryon acoustic oscillations, often shortened to BAO. The name sounds technical, but the idea can be carried gently. In the early universe, before stars formed, everything was hot, dense, and filled with light. Ordinary matter, protons and electrons, was coupled to radiation. Photons and matter pushed and pulled each other in a kind of shimmering pressure wave. These waves expanded outward from tiny overdensities, like ripples in a pond, except the pond was the universe itself. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral atoms. Light decoupled from matter. The pressure waves stopped being driven, but their imprint remained. A slight preference, a faint ring of separation scale where galaxies would later be a little more likely to form because matter had been nudged outward in those ancient ripples. Today, billions of years later, that ancient scale still exists as a statistical feature in the distribution of galaxies. It is not visible as a ring you can point to in the sky, but it appears in the way galaxies cluster and in the typical separation between large-scale structures. Cosmologists use this as a standard ruler. If you know the true size of that ruler, you can compare it to how large it appears at different distances and learn how the universe has expanded over time. Now, here is where voids quietly return to the story. Voids are not separate from BAO, they're part of the same large-scale landscape. The cosmic web is a combination of overdense filaments and clusters and underdense voids between them. When surveys map galaxies across enormous volumes, they are mapping both structure and emptiness at once. And because voids grow and shift with expansion, their statistics can complement BAO measurements. This is a very gentle but important point. We do not learn cosmology from a single object. We learn it from the way millions of objects and millions of empty regions arrange themselves. In that sense, the Great Void is not just a feature, it is part of the cosmic measuring apparatus. Modern surveys, like the Sloan Digital Sky Survey and others that followed, have used BAO to trace expansion and also identified vast catalogs of voids. Together, these approaches help constrain dark energy. They help answer whether the expansion history matches a cosmological constant or something that evolves. The story is still unfolding, and future surveys will deepen it. But even now, the overall picture is surprisingly consistent. The universe expands, and the expansion accelerates. Void by void, ruler by ruler, the measurements point toward the same quiet conclusion. Still, there is another layer of measurement that suits the Great Void more directly. Weak gravitational lensing. In dense regions, lensing can be dramatic, bright arcs, multiple images, strong distortions. But in voids, lensing becomes subtle. The mass is lower, so the bending is weaker, and the distortions are small. Yet, when we stack the signal from many voids, a pattern emerges. Background galaxies appear ever so slightly stretched in a way that reveals how mass is distributed around and within voids. This matters because lensing responds to all mass, not just what shines. It tells us about dark matter in regions where galaxies are scarce, and it also helps test whether gravity behaves as expected. If you imagine it quietly, it's like looking at a distant landscape through very thin glass, so thin you don't notice it at first. But when you examine carefully, you realize the glass has a gentle curve, and that curve carries information. Voids bend light less than clusters, but they still bend light. Even emptiness has weight, because emptiness is never perfectly empty. Now there is an even quieter measurement, one that may feel almost like listening to a tide. Cosmic flows. Galaxies do not only drift with expansion, they also move in response to gravity, toward overdense regions, away from underdense ones. Voids, being underdense, create an outward flow. Matter slowly drains away from void interiors toward their boundaries, toward the filaments where gravity is stronger. By measuring galaxy motion statistically, astronomers can estimate how fast structure grows. And structure growth is sensitive to both dark matter and dark energy. If dark energy were stronger in the past, structure would have grown differently. If gravity were modified, flows around voids would look different. These are delicate measurements, full of noise and uncertainty, but they improve each year as surveys grow larger and instruments become more precise. What emerges is a kind of calm mosaic. BAO gives us a ruler. Lensing gives us mass maps. Cosmic flows give us motion. And voids weave through all three, not as empty mistakes, but as central features of the universe's architecture. If you pause here, you might notice something quietly profound. The universe allows us to learn its history without ever touching it. We infer the invisible through patterns in the visible, and even through patterns in what is barely visible. It's not unlike listening to a distant ocean at night. You can't see every wave, but you can hear the rhythm, and from the rhythm you understand that the ocean is there, moving even in darkness. So, here's a question for you, one you can answer with a simple feeling. When you hear that scientists measured dark energy using rulers, distortions, and flows, does it feel like certainty, or does it feel like a careful kind of faith in evidence? And when you imagine the great void, does it feel empty, or does it feel structured, quietly shaped by laws you can't see? If you'd like, share your sense in the comments below. A short sentence is enough. In the next file, we will bring the great void closer to home, not in distance, but in perspective.
Now that we have wandered through evidence, patterns, and the quiet geometry of emptiness, it is natural to ask what all of this means on a human scale. Not in usefulness, not in technology, not in practical advantage, but in perspective. The great void is distant, vast beyond instinct, yet it changes something subtle in the way we imagine reality. Because once you realize that most of the universe's volume is empty, and that this emptiness is not an accident, but a fundamental feature, you start to see the cosmos differently. We often picture the universe as a collection of objects, stars, galaxies, nebulae, planets. But the universe is not mostly objects, it is mostly space. And space is not simply a background, it has geometry, it expands, it carries energy in ways we do not fully understand. It shapes what matter can do, where it can gather, how it can evolve. The great void is space showing itself as a dominant presence, not through brightness, but through the absence of brightness. In a void, you do not lose the universe, you lose the distractions. You see what remains when the cosmos is stripped down to its most basic motions: expansion, gravity, time. This is why voids can feel strangely meditative. They reduce the cosmic scene to the slowest, largest rhythms. When you imagine drifting there, you begin to sense that the universe does not rush. It does not hurry toward conclusions. It unfolds. And that unfolding is often quieter than our minds expect. There is a delicate contrast here that cosmology keeps revealing. On small scales, the universe is turbulent. Stars flare, planets form, life emerges. Cells divide, nervous systems create thought. All of this is energetic, complex, dense with events. On large scales, the universe is calm. Structures shift slowly, distances widen gently, voids expand like a long breath. Both scales are real, both are true at the same time. And the great void sits at the intersection, reminding us that existence happens in islands of matter surrounded by vast silence. There is another quiet lesson in this. The universe can be meaningful without being crowded. It can be structured without being filled. And perhaps this challenges how we think about emptiness in our own lives. We often treat emptiness as something to avoid, a blank calendar, a silent room, a pause between tasks. We fill it quickly, we distract ourselves. But the cosmos seems to treat emptiness differently. In cosmic evolution, emptiness is not failure, it is the canvas on which structure appears. Without empty space, there is no distance, no time for light to travel, no room for galaxies to form as separate entities, no calm background against which patterns can be measured. The great void is not a gap in reality, it is part of reality's design. Now, there is a speculative thought that sometimes appears in discussions of the far future. As dark energy continues to accelerate, more and more of the universe will become unreachable.
not because it disappears, but because the space between regions expands faster than light can cross it. This creates a kind of cosmic horizon. In the far future, distant galaxies will slip beyond that horizon. They will fade, their light stretched longer and longer until it becomes too faint to detect. A future civilization, if it exists, might look outward and see only its local gravitational island. The rest of the universe would be invisible, not because it is gone, but because expansion has separated it beyond communication. In that sense, the universe itself could become a great void for any observer, not absolutely empty, but observationally empty, a quiet, sealed bubble of space-time. This thought can feel strange, yet it is also a reminder that our current cosmic era is special. We live at a time when the universe is still readable. We can still see distant galaxies. We can still measure the cosmic microwave background. We can still reconstruct the history of expansion. We are not at the beginning, and we are not at the end. We are in a middle moment when the cosmos is still illuminated enough to be understood. That alone is worth a pause. If you reflect on that, what arises? Gratitude? A sense of smallness? A sense of wonder? If you feel like sharing, you can write a simple comment below. What does it mean to you that we live in an era where the universe can still be mapped? And if you prefer to keep the thought private, that is fine too. The great void does not demand answers, it offers space for them. As we near the end of this episode, let's return to the central image, a universe made mostly of unseen components, dark matter, dark energy, and the vast expanding emptiness between structures. Within that universe, our galaxy is a small luminous island. Our planet is a smaller one. Our lives are brief, yet capable of understanding scales far beyond themselves. That is not nothing. It is, in its own quiet way, extraordinary. In the next segment of this series, we can follow the void into new questions. Are there different kinds of voids? Could some hide subtle dark matter substructure? Could voids help us test the nature of dark energy more directly? Could the quietest places in the cosmos be the best places to look for new physics? For now, let the great void remain what it is, a silence with structure, an emptiness with geometry, a long, slow breath of space-time carrying everything outward, without urgency, without noise. And as you listen, and as the images drift gently across your screen, you can simply rest inside that thought. The universe is vast, mostly empty, and still beautifully ordered.